Hello community, so great that you are back. Yeah, today we are back Discover AI, your channel with the latest AI research. And today I say, hey, come on, we talked here about weeks now for LLM reasoning. So now let's discover some new places. No, come on over, let's cross together here the Roman Limes and let's discover some unexplored land like multimodal reasoning. And of course, what I expect is, hey, if text reasoning was so great, imagine if I just audio and then have text audio reasoning, it must be so much better. And then if I have a complete video stream with everything, then reasoning will be simply a delight. No, this is my expectation, and just to make it clear, I say, okay, just for test reasoning, let's do this. I have here my transformer, and I have 3 input channels. Here I have pure text input stream, an audio input stream, and a video input stream, just to make sure that I can really here distinguish between the different modalities. Now, what's really gonna happen now is, interestingly, imagine you have a text input stream that is not really 100% coherent with your audio stream, and video shows a little bit different topic in general, so the AI has now to do a decision process which of those 3 channels provide here the correct information. Multimodal reasoning. So let's expand here AI beyond text, integrate vision, audio, and other sensory data. So the reasoning process encounters now some tiny little problems. And this is situations where distinct here channels yield contradictory evidence. Now the fun begins. Because you know what? What is the reality? If we do this, you have a text performance, you have an audio performance that is counterproductive to the text intelligence, and the video intelligence is going somewhere completely else. Now let's explain this, but before that can I tell you, it is even a little bit more complicated because we do have oscillations. Because even for audio and video reasoning, we do have reasoning oscillations within the transformer layers, and even different layers of the transformer have different oscillation at different points in the reasoning process. So this is gonna be a lot of fun to explore. Can you imagine this would happen here in multimodal reasoning? So let's start the video, and first we need data set. No, we need data to evaluate. So we have 3 unique video data sets. So the first one is here from June 2019, multimodal multi-party dataset for emotion recognition in conversation, Singapore, Mexico, US, beautiful. So what they did, they went to the TV series Friends, and they simply extracted 13,000 utterances from more than 1,400 different scenes from dialogue here from the TV series Friends. So they have audiovisual and textual modalities, which is great. So here you see it here, the dialogue between 2 of the actors here, and you have everything that you need to compare this, feed this into an AI and see what happens. But of course, we also have, if you want to have it much more detailed and you just want to focus here on the face and a little bit on the arms. So we have 50 markers here on the face in this particular study here from 2007, interactive emotional dyadic motion capture database. My goodness, I have really to go to ResearchGate to find this publication. And then, of course, we have here multi-label learning, modality robustness, and semi-supervised learning challenge here, MER 2023, and all those beautiful people contributed to this. Let's say those are our data sets. This is what we have, and now let's start and examine this. So I would assume no classical AI fusion data streams. I have an additive information gain, as I showed you. 3 arrows up, beautiful. But the reality is often, as the authors will tell us from the first study, a non-linear interference. We will have a dominance factor, so one modality, often this is the pure text, will suppress the influence of the others, especially audio and video. We will have a collapse in the mode, in the modalities. So we have one stream saturates here the joint embeddings completely. And we have a little espionage, sabotage here. because we will have a confident but completely incorrect wrong modality that simply overrides here the complete ensemble. And you would say, how is this possible in AI? No? We have super hyper intelligence. How can this happen? Now let's have a look. Let's start with a first perspective. Let's frame this here on a pure theoretical layer. No? Modeling conflict as a function of relative uncertainty. Let's be scientific. And here we have at Harvard University and MIT Media Lab, published just 2 days ago, November 4th, 2025, when one modality sabotaged the other modalities. A diagnostic lens on multimodal reasoning. And the title gives you a hint. This is gonna be interesting. So let's start. So the main idea is you have a model's choice of which modality to follow in a conflicting situation is now governed here by the relative reasoning uncertainty between the unimodal predictions modulated by an inherent preference parameter. I will show you this is true. Please notice that we are talking about a relative reasoning uncertainty, and we have a fixed parameter for each model, an inherent preference parameter. Let's explore this. So if we look now here at a specific heat map where we have now the modality, here the first column you have text, the second column audio, the third column you have vision or video, and then all three together. And then we have here all our three data sets I just showed you, and then we have a look, hey, what about the accuracy? What happens here? Unimodal accuracy for text, audio, vision. Look how different this performance is for three different data sets. Here, text is here beautiful, accurate here at 50% for this data set, but only at 18% for the first data set. And here, video is beautiful, accurate 50% for the first data set, but for the third data set, it is only 17%. So you see, oh my goodness, something is going on. But let's make it a little bit more interesting, no? Let's do a little bit of espionage here, the sabotage cases. So you see, dark red is going up to 100% sabotage cases here. So let's have here we have the same modality, the same X and Y axis. So what we have? We have here the number of cases, or the total of cases, and the percentage rate. And you see here, audio sabotages here beautifully more than 60% of all the cases for the first data set. It sabotages close to 60% for the third data set and only quotation mark, 48% for the second data set. So you see, unbelievable, but think about it. Just if you add audio to your text, audio will sabotage the performance of your system in more than 60% of the cases. Why is this gonna happen? What happened to our beautiful AI that was trained as a large language model on written linguistic text segments? Welcome to our second study. Look at this, also November 4th, 2025, when modalities conflict. So now we have the conflict, an open conflict between the single modalities in a multimodal AI system. And we want to understand what is happening. How unimodal reasoning uncertainty governs here the preference dynamics in MLLMs. And we have here Peking University, I love this title, Prada Lab, the Provable Reasonable AI and Data Analytic Prada Lab. I will publish something in very shortly, maybe with a Ferrari lab or a Lamborghini lab. Just have to find here the title. And then we have Tsinghua University, University of Georgia, beautiful. So really interesting, real powerful teams come together. So what do? They say a critical challenge arises when the modality present conflicting information. And I showed you this in my image when we have three different input channels to our transform architecture. And they make a simple example. Now, an image might show a blue car, while the accompanying text for the multimodal input describes the car as a red car. And you might say, okay, no problem, no? Yeah, but which input modality does your LLM now prefer and says this makes the decision that this is the correct one and output this one? So they say in those cases where the MLLM must resolve the conflict leading to an observable behavior, we term this the modality following. Do you go with the blue car or with the red car, with the image or with the text? So the model's final output aligns now with the information from one modality over the other. So here we have it. Some of the models, and it turns out almost all of the models, do have an irreplaceable priority. And a lot of them will go with text because we started with a large language model and then we just added here vision as a feature. And only in very few cases we started here with the visual transformer architecture and then added on top of it, the cherry on top, was the large language data. So let's have a look at this. And I made a very simple example. Look at this. What is now the most important fact in this second study is that we talk now about dynamic reasoning difficulties. And in two manifolds. No? The first is here text, and the second is visual. And here we have it. So the question is simple. No? For all cases, what color is the square? And now we say, let's build different reasoning difficulties for visual. So the first visual input is here a single, let's call it a square rectangle that has the color red. Let's increase the complexity a little bit. So we have the red square, but other objects in the image. So we have to do a segmentation and so on. And then let's go to an even higher complexity that there are some objects in front of our red square. So it's not so easy to understand where is the shape of a square and identify the color. But at the same time, we have this increasing reasoning complexity here also in the textual input. The first sentence is the square is blue, which is, if you look at this visual, not really the case, no? And then we have the color of the square, and now a little bit for the LLM thinking, is the same as a sapphire. And a sapphire is blue. So you see, chain of thought, so the color of the square is blue. So the same content, yeah? And then we have something like, hey, the square has the same color as a morpho butterfly wings. I have no idea what it is, so I hope you know it. But let's say it is blue. And now they measure here the uncertainty measure of an unimodal element. Multi-modal large language model is an acronym in itself where you can smile about it, but never mind. So what you see, you have now to find here a particular parameter, a particular feature from theoretical physics that we say, okay, this is here for visual and this is here our parameter for text. And as you see already, we are working on a probability distribution, so visual and text, they are somewhere different in the probability distribution itself. And then we can define something like a relative uncertainty parameter. Yeah, simplest cases is delta H, relative, and then we see, hey, does the system prefer text or vision? You see, we've just built different reasoning complexity, difficulties, and the reasoning process can start. So what do you think? What is going to happen? And they say, we notice, and I give you kind of a result already, we have to work with relative reasoning uncertainty. So we have to work with case-specific confidence gaps between different unimodal predictions. And we have an inherent modality preference, like I already showed you. We have a model's stable bias when uncertainties are balanced. So this means if we are exactly at a 50-50 chance of text to visual, then the model inherent internal bias will decide. But at first, let's look here at the first term, the relative reasoning uncertainty for a multimodal reasoning exercise. What is this? Now, those are computer scientists, and so they had to find a parameter. Now, if you were theoretical physics, you know it is entropy, of course. I mean, what else? But if you read the study, and please do read the study, it's a beautiful study, enjoy it. You find, the authors found here, guess what? It is an entropy that what we are looking for. And in unimodal entropy trends across difficulty tiers, you see here for the text modality, the difficulty level is increasing. If you go to the right-hand side here of the x-axis, and on the y-axis, we have the average entropy in some corrected cases, never mind. But you see, so in text and in vision, the modalities, if we use the entropy, this is consistent with the increases with difficulty validating its use as entropy now as the proxy for a model perceived uncertainty therefore revealing here differences in the model capabilities. Okay, we have now exactly what we need. We have our metric that we can analyze, and it is here the entropy. Now, as I told you, of course, we take some real old stuff, no, because God forbid that we would take here the latest multimodal models and show that they are not perfect. I mean, the whole US economy would just crash and crumble down to pieces. So we take here an old Lava 1.5, or Lava 1.67b, a Lava 1.613b, and a QN 2.5, not the 3, no, the 2.5 Vision Language 7b, and even a QN 2 Vision Language 7b. And you see, all those models have different characteristics in their modality following ratios. And as you can see, blue is they prefer to follow the text in their decision making. Look at the blue, all above 50, and then we have only 2 models that are below 50, and here we have the vision. The red bar is here. The vision dominates the decision making internal mechanism of this AI model. So we have here with 70% and here close to 90% here in the very old QN2 version, Vision Language 7b. So this was really built, as you can see here, on a strong focus on vision performance. And a little bit was textual. And now you might ask, why do those AI models exhibit such divergent and seemingly fixed preferences when evaluated on the same dataset? And they found out the core flaw in the macro level statistics here, like the TFR, is that they ignore the case-by-case reasoning confidence. So you just can go with statistics. You really have to go case by case for each and every particular model. So to capture this, the authors now came up with the brilliant idea to go with you know this already, a relative uncertainty. A relative unimodal uncertainty that we measure, surprise, surprise, with the entropy parameter, and we have now a relative entropy delta that will help us to understand what is going on in those models. So here we go. We have now a relative reasoning uncertainty defined using here the output entropy as a measure for the perceived uncertainty in unimodal reasoning. If you're not really familiar with this, here we have now the delta H relative. Here is exactly this formula from theoretical physics or statistics, of course, where HT are the entropies for the text only and HV are the entropies for vision only reasoning. And if you have here a minus divided by a plus, you get exactly our delta H that we're looking for. And if you say, hey, what were the formula for entropies? Of course, here I provide this information for you. So this means the probability in general to follow the text monotonically decreases here as the delta H relative increases. And they found this to be an empirical law that holds across model families, scales, and architecture. And they dare to say, you know, we found a universal control principle. I'm not sure, but okay, for some model, there is kind of an empirical law that models dynamically allocate the trust. Trust is a human word, but you understand what I mean. A highest probability sequence across modalities based on comparative uncertainty. Not on a fixed preference. The fixed preference is only an additional second-order correlation term, but primarily we have comparative relative uncertainty for the reasoning process. Great. So let's play with this. So we have now a new metric. Our delta H relative quantifies the model's perceived confidence gap for each specific output. It's a direct manifestation of the model's unimodal capabilities shaped by its architecture and the pre-training data and everything, of course. Now, what does a negative value mean? This indicates that the model is more confident in the text, while a positive value means, see the formula, that it is more confident in the vision. If I print now the relative uncertainty here, I have here my 0 and I have here the negative and I have here the positive. And I look here at all my beautiful lava models and QN 2.5 and Q2, you see the old one here is really here, definitely here with a positive value here on visual. But look, the others are almost looking here relatively the same. No? So this means a new puzzle emerges, no? Despite the different macro-level behaviors, most models face a similar distribution here, skewed towards negative values here. Here you have -1, -2, meaning the dataset is, on average, easier for them to process through the text. Of course, it is an LLM, it was at the beginning an LLM that we just then added here on top of. But this kind of deepens the mystery, yeah? If the underlying difficulty distribution is similar for the most models, why are their final choices so different? Look, all those distributions look rather similar. So what is their criteria that we have? The end result, the final choices are completely different. Something else is going on, much deeper in the transformer architecture. And here we found it. Yes, if we have now, we print the relative uncertainty on the x-axis. Remember, in the middle we have 0, and then we have here on the left side the negative, on the right side the positive, the same as here. And now we have a new parameter. This is called the text preference ratio, TPR. And yes, even the authors of an archive paper can make here a typing mistake because it's not TRP, but TPR. Now let's look at those representations. Now they look real similar. Look, we have 6 models and we have, almost 6, very similar curves. So what is happening here? Why we have here our 50% mark exactly indicated? This is now something that we can work with. And we say by plotting now the probability of a model following in the text modality against the corresponding delta H relative for each case, the apparent chaos resolves into a single unified pattern. Look how beautiful monotonically decrease our curves are, all of them. If you go high entropy, low entropy, balanced, unbalanced, look at this. And you say, okay, let's play with this. So what we have 2 thresholds. No? The first here is exactly here, the relative uncertainty is 0. This means the negative and the positive, and what happens at 0. And then we have this text preference ratio at 50%. So if it's really 50-50, 50% text and 50% vision, what happens at those places? Why they seem to be of importance? Let's have a little bit of a deep dive. So for all of their model that they calculated, the author tells us, no? Regardless of the architecture of the scale, we see here a smooth, monotonic decrease in all those indicators. In other words, as the text becomes harder relative to the vision, so this means the delta H relative increases going to the right-hand side, the probability that the model followed the text steadily and predictably decreases. Remember, we started with different difficulty levels, with different complexity levels on the text manifold and on the vision manifold. And now we say, as the text becomes harder to understand, to interpret, to reason, and we have a very simple visual representation of some context, the model now inherently trying now to find here a solution, an answer to be helpful. Remember the system prompt. Now the model switches from a predominantly oriented text dominance to a vision dominance, because now the text complexity for the reasoning goes over a threshold and becomes too difficult to proceed. And now the internal AI model says, hey, let's go with vision. This is much easier for me to understand. So now I trust vision. So you see, this steadily and decreasing probabilities give us some beautiful information. But it also tells us that, and this is the central hypothesis here, that the modality following is not fixed. There's only a small little piece that is fixed. But in general, the modality following is a dynamic behavior governed by relative reasoning uncertainty for each particular model, for each particular query, for each particular domain complexity, for each completely different complexity in text, for each completely different complexity in vision, and then in video. So you say, oh wow, what a pleasure. Okay, so with all models obeying this monotonic law, everybody goes down, their curves are positioned differently along the axis, no? And this leads now to the second key insight the author tells us. And they define now the balance point, exactly at the 50% mark. And at this balance point, as the delta H relative value at which the model is equally likely to follow either modality, this is not a balance point. And yes, you guessed that the balance point is important for the reasoning oscillations I introduced you at the very beginning of this video. So now we are coming here to the deeper explanation why this is happening. Now a balance point below zero, and remember this is the left half of the graph, indicates here an inherent vision preference. Why? As the text must be significantly easier to be treated as equal, while a point above zero, this is on the right side, indicates an inherent text preference. So with this understanding, we finally understand, or this allows us to disentangle here a model's fluid in the moment decision making from its stable underlying bias. So remember, we have a big chunk that is here dynamic and a little chunk that is here the stable underlying bias of the model itself. And normally, a lot of models prefer here the text predominant augmentation. So you see, this balance point becomes now really important because now we have a deep dive on those balance points. And now we want to understand what is happening inside of the transformer, inside of our AI, when they have to do a decision. So vision input is this one. We have our red square in the middle. And then the text input has three different complexities. The easiest one, the rectangle, is blue. Now, since we have no rectangle, this is an interesting piece of information. Eh? Then we increase this a little bit. The rectangle color is the same as the pentagon, and the pentagon is blue. And you say, oh wow, this really helps a lot. Eh? And then the rectangle color is the same as a peacock neck. And now what they did, yeah, they have the heat map across the layers. But what's really nice here, look, on the x-axis you have here the layers, how deep we are into the reasoning process, in the transformer architecture itself, in the, if you want, layer structure. And then we have here the logit differences. Now the logit differences are calculated as the logit of the text answer minus the logit of the vision answer. And now you say, oh, I see. So where does the, with quotation mark, decision making happening? So in the first shallow layers from 0 to 10, yeah, you do have oscillations, okay? So maybe it's yeah, no, vision, text, vision. But then for the easiest one, the rectangle is blue. Well, okay, this is also theoretically, a square is also kind of a deformed rectangle. So you go, okay, so we go here, the blue line. So we have a decision. So if we go now with dt, so the difficult level here of the text equals 2, so the maximum amount that we have here. So you see here red, and then, yeah, okay, it's clearly separating here. Okay, also we have a clear decision that happened here, internal, let's say, layer depth 22, 25, 30. Here it's gonna happen. Here the AI says, and now I believe in whatever. And then we have the case here, the complexity level here from the text at 1, where you see we are above 0, here the gray line, and then we go below 0, then we go above 0, then we go below 0, and here you can see, the system is not sure. The system is oscillating here. For the one moment it trusts the text more, for the second moment it trusts the vision more, and it is absolutely oscillating. Now for us user this is great, because I will get then the answer, hey, this square is red, this square is blue, this square is violet, this square is white, this square is pink. So if you get this, this is not that you coded something wrong. This is an effect of the current way how we build vision language models and the problems we encounter with them if you really have a deep dive and you try to understand, if you have different vision input to a text input, which input stream is going to win over the other one. And this is specific for each model, for each complexity level of vision and or text. So I found this really interesting because it tells me, interestingly, so in the deeper layers, so if we now build our next AI generation models, we understand that we can have here some interesting new mathematical formulas, and you know what I mean, to have here a clearer picture. And maybe we can even have an output that we understand, a reasoning process of the model that tells us, hey, given I have here a discrepancy, I go now with text, or I go now with vision, and those are the reason for my decision. So you see, beautiful, but it also tells you we are right at the beginning. So this oscillation is something absolutely fascinating. An AI that cannot make up its mind, and you deepen the layer structure, it goes from yes, no, yes, no, yes, no. So absolutely. So it switches from a vision-supported answer to a text-supported answer, vice versa, regardless here of the intermittent prediction of irrelevant tokens. So what are the conclusions? Apart that we have a lot of work to do for vision language models. The authors tell us we uncovered a law. Well, they uncovered a relation for certain models, no? The likelihood of following a modality monotonically decreases as its relative uncertainty grows, underscore relative uncertainty, with the balance point offering a principal measure of inherent preference. Beautiful. Now we understand, we can check an AI model and understand what is the inherent preference, text or visual. And probing layer-wise predictions further revealed that in some regions that are near to this balance point, the model exhibits strong oscillation between the modalities, directly explaining here the output result by those models. But this is more or less what we expected, no? But now we pinpointed those balance points. Now we can even calculate the balance point, and we can maybe calculate also the epsilon environment around those balance points where we expect some oscillations to happen. So if your model produces here at second 12 the result A and second 13 the result B, you understand it is not your fault. This is just an output by the AI system in the way we built and trained it. But this gives us here an insight that this preprint, let's call it reframes here, the multimodal reasoning as something completely different. Yeah? Because I see it now as a stochastic dynamical system that is driven by an uncertainty gradient between the modalities, like we have seen in vision and text, and in general, a strong bias term, depending on your model, representing an inherent preference. I showed you 4 of the 6 models had text, and 2 of the 6 models had vision, inherent preferences, because that's the way they were built. They came out of the fabric here in this particular way. And this perspective now introduces here a control theoretic analogy. No? Because what is the uncertainty? Uncertainty acts now as a damping term. The preferences are as a kind of an equilibrium offset, and the oscillation that we have on around the balance points as a resonance phenomenon of competing evidence. This is absolutely interesting. Suddenly I have so many ideas, so many formulas from theoretical physics I could apply to each of those 3 elements to further advance here the development of the next generation AI models. But I just hope I've given you an idea. If you have a little bit of a deep dive in multimodal reasoning, you see exactly where are our border of knowledge and where do we fail. I hope you enjoyed it. I hope you had a little bit of fun. Subscribe, become a member, and I see you in my next one.